Good evening. So first, I'd like to introduce my team members and Abul Fasal Masumdar and Dr. Kyle, uh, both here. Okay. So Abul is my PhD student and Dr. Kyle is the professor in Department of Engineering, Design, Manufacturing and Systems. So I'll skip the outline because of the time. So right now we had so many presentations explaining like what they are doing in order to improve. I mean, cycling, walking, and all. So when you go into cycling, now they are looking at complete street policies and all the sort of things to promote them. So when we try to integrate bicycle facilities, we have several options. Like Rebecca from the city, she explained what options they have. So one is basically we integrate the bicycle lanes within the same roadway. In that case, we are limited with the design. I mean, controlling the design parameters. Okay. We have to deal with the existing curves, super elevation, okay, transition curves, and all these. But the other option is to have a separate bike path. In that case, we have little more flexibility in designing the roadway width, the curve, and the transition curve, slopes, all these to control the stability of the bicycle and also improve the rider comfort. So that's actually the focus of our work to evaluate impact of roadway design parameters on bicycle stability and the comfort of the rider. So right now, if we look at how people are evaluating this, they do the surveys, they take video recordings to understand how the bicycle riders are responding to different obstacles, different curves, or the roadway design parameters, as well as they are doing this to evaluate how the drivers are responding to the bicycle. Okay, so but our focus, I mean, these are great tools, but it needs a lot of resources. Okay, so what our thinking was, can we develop some simulation models, computer simulation models, to get a bicycle traveling along a predefined path and try to understand what are the forces developed in the system and how to make the bicycle stable. So what is the stable velocity for a given road configuration? And as you go from straight roadway into a curve, what are the forces going to develop and how it will make the rider comfortable or uncomfortable? So that's the focus. So with that, came up with this idea, and it was because mainly I worked with Dr. Kyle several years ago developing vehicle models. So we developed complete vehicle models like Hummers, flatbed trailers, and also the semi trailers. And what we were doing is I was developing the model, and Dr. Kyle is expert in vehicle dynamics. So he was simulating these vehicles on different road profiles to understand the stability of these vehicles. Okay, as you drive around a curve, what is the minimum curve that will cause the wheels to lift? Okay. And also we were doing some durability studies. So we were running the vehicles on different road surface conditions to understand the stresses and strains developed in components to find out how long these components are going to survive under these road conditions. So with that background, we thought, why can't we develop a bicycle model and try to evaluate the design impact of design parameters, okay, on the stability and the comfort of the ride. So we did a thorough literature review to understand the state of practice, state of the art, and then we work on a specific software that allows us to develop the bicycle model. Okay. And then we did some evaluation of the impact of these parameters on stability and the comfort of the rider. And based on that, we are proposing some recommendations to move forward with this research. So there are so many different parameters that we need to consider for bike path design or bikeway design. So out from those, for this study, we were looking at the design speed, the horizontal curve, radius or curvature, and possibly including friction, and also we look at the impact of the transition curves. As we enter the main curve, how we can use the transition curve to reduce minimize the forces and the discomfort. So if you look at someone riding a bicycle on a horizontal surface with a curve, it develops several forces. One, that person is going to have its own, including the bicycle, the body weight and the bicycle weight acting towards the ground. and the other force is going to be because of the we call the centripetal acceleration that works outward of the curve. Okay, that's normally acts to the center of gravity. In addition to that, we are going to have some forces develop at the road and the bicycle tire interface. Okay, you will have a normal force and a friction force. Combine that, we are going to have a resultant force that passes through the center of gravity. Okay. So those who have done basic statics, okay, you will know that if we have three forces that pass through the a point, you can represent that with a closed form triangle. And if you can make that triangle closed, that means the system is in equilibrium. Okay. In order to happen that, we have to have what we call the lean angle. Okay. So by looking at all the forces developed, we can calculate what is the lean angle with respect to velocity and radius to make this bicycle stable. If you are riding on a road with a super elevation, we also can look at the influence parameters. So those are the velocity, friction, super elevation rate, and also includes the gravitational acceleration. So with all these forces, okay, involved, so we know the equations and the parameters, but our focus is for the including limited number of parameters for the analysis. Okay, there are limitations that I'm going to discuss later. So with our approach, we use the horizontal curvature, radius, speed, and transition curves, in addition to the forces going to develop in the system. Okay. Our simulation was right now with the horizontal curve on a flat road. So we developed the bicycle model, but developing a bicycle model, okay, has a long history. It has been done more than a century ago. Okay. So people developed this model in 1899, which has four components: front wheel, the rear frame with the rider's mass, and then the front handle and the axles. So we were planning to incorporate this, and also we look at what is the recent development. So people developed the basic model, then it was updated by incorporating additional parameters into this model in 1987. But I call Papadopoulos, okay. So improve the model. So now having the dynamic model with all these parameters, okay. So all these parameters are listed in this table. So there's like 25 different parameters. We can calculate the stable velocity region, okay, for a bicycle. You know that as you have ridden the bicycles, so if you go at a slow speed, you're going through kind of wavy mode, and then if you don't balance, you're going to fall down. If you have riding it at a very high speed, okay, you may feel it's going to be stable now, but after certain speed, it will start, okay, shaking, and then you lose the stability. So that's what we are showing here. So you can calculate the self-stability velocity region. So these are used to validate our model. Okay, so we try to use the existing parameters and the fundamental model to validate our model. So what we did in the computer, we developed this model. So it has again two wheels, rear frame, and the front the what's called the fork and the handle. And difference between this model and a typical analytical model is this one has the distributed mass except the rider. Okay, so all the components are modeled with their mass and the material properties. Then in order to control the stability, right now we have constrained the points of the wheel that touches the curve so that we can allow this bicycle to follow a predefined curve. Okay. After we were successful that, what we did was we removed the constraint provided at the rear wheel, and we were trying to find out as you ride the bicycle, okay, when the rear wheel is going to slip out of along the plane. So that's where we can introduce friction and try to understand the impact of friction. So we developed the model in computer, but we didn't have all the parameters available in literature. So based on the geometry that we developed, we had to modify some of the parameters that change the stable velocity region, okay, that we calculated. So we recalculated them based on the parameters that we already included in the model. After that, we wanted to simulate this bicycle uh, the what's called the movement along a predefined curve. So TRCLC has an instrumented bicycle. They collected a lot of data by allowing people to ride on this path. Okay. So what we did was we went to Google, got the map. So we started fitting a curve for this route. So that gave us the straight portions of the road and also the different curves with different degrees of curvature. So we input that into the computer model and then try to get the bicycle following this path to understand what are the forces going to develop in the system. So this is showing how it was integrated into the computer, and then we were running the bicycle model, I mean getting the bicycle moving at different velocities, okay, within the stable region. So there are like the thick line is showing what is the real path defined in the computer model. Okay. And then there are some small straight lines, those are just graphical kinks, we can say. Okay. So then what we got? Okay, so now you see this straight part, that's just graphics. But if you simulate the bicycle, it's going to follow the real curve. So you may see it's going out from that straight path because the reason is the real curve is this one. So the bicycle is following that curve. The other one is just graphical issue. Okay. So now we have the complete model developed. So now we can simulate it following the curve. So even though it's going out, it's really not going out. So it's following the predefined path. So in this particular case, we left the rear wheel and front wheel both constrained to follow the predefined curve. So there's no slip because both wheels have to follow the same path. So next stage, what we did was we released the rear wheel and got the bicycle to follow the same path. And as you can see over here, what's going to happen as the bicycle enters the curve, you'll see some slip in the rear wheel. Okay? And as it exits the curve and get into the next part of the road, you'll see some slip happening at the rear wheel. Okay? So this is showing the position and the slip angle of the rear wheel. So we were successful in doing this. Okay? But the results that I'm going to present to you is only coming out from the first model where we had both wheels constrained to the path. So initially we verified all the loads acting on the wheels as a verification process. Okay. And this is what you're going to see. What you see over here, we have the centrifugal acceleration as the vertical axis and the time as the horizontal axis. So as the bicycle travels along different curves, we can measure the centrifugal acceleration. So as you can see, in certain cases, okay, it's a little higher, and some other cases were lower. So it depends on the curvature as well as, okay, this has a constant velocity. So it's basically based on the degree of curvature. Okay. After that, we look at what's going to happen when the bicycle enters the curve and exits the curve. So that's where you see the jerk. Okay, jerk is the change in acceleration with respect to time. So these vertical axes are not in the same scale because we wanted to expand for clarity and show how the jerk is going to change. So the first curve has vertical axis maximum 45, but the last one is like a jerk of 600 close to. Okay, so it depends on what is the curve before the real curve. Okay, that's not really the transition curve here in the path. Okay, we can say that's a transition curve. So what is the change in curvature between the start and the real curve? So based on that, we can see there's a large jerk acting on the rider. So that makes the rider uncomfortable. So what we did was we calculated the length of the transition curve. So we included that into the model. So now you can see the same curve with the transition curve, you can minimize the jerk acting on the bicycle or the rider. So with this, we can evaluate the impact of these parameters, roadway design parameters. Right now, we have limited parameters included, but we are trying to modify the model to have more degrees of freedoms released to even find what is the lean angle, okay, whether we can capture the lean angle. How we can use this? Okay. I'm going to skip some of the slides. Okay. So how we can use it? If we have an existing road and we want to incorporate a bicycle lane, we can take the parameters and try to find out how that will impact, okay, or what is the influence of those parameters for the stability of the bicycle and the rider comfort. If we are going to design like separate path, now we have the flexibility to change the parameters, so we can evaluate lower bound and upper bound values and try to stick with that. So right now we have a couple limitations in the model. That's the tying the wheels to follow same curve, but we have released the rear wheel and we look at the impact of that on slip. Okay, most probably we'll be able to incorporate friction. So the next step in our work is really to look at, okay, how to fine tune this model to capture a roadway design parameters impact on the stability and the rider comfort. So with that, I'm going to thank Dr. O and TRCLC group for funding our work, and also our team for doing excellent work. Actually, this took a lot of time and effort, okay, starting from scratch within a year to complete this model. With that, I open the floor for questions. Thank you.